Today we will be learning about special right triangles. One thing that makes these triangles so special is how much they are used in construction. The roof of a typical home is almost always either a 30-60-90 triangle or a 45-45-90 triangle. When using 30-60-90 triangles, they actually use two of them next to each other. So you have a 30-degree angle, a 30-degree angle, a 60, and then your 90s, which means the angle at the peak of the roof is actually 120 degrees. On the 45-45-90 triangle, the peak of the roof is your 90-degree angle, and then the two 45-degree angles are at the eaves. We're going to start with the 30-60-90 triangle. It's helpful to know where the parent triangle comes from when we work with these. So we're going to start with an equilateral triangle. Now we remember from earlier that an equilateral triangle has three 60-degree angles in it, and if we take one vertex and draw the altitude in it, it divides it into two 30-degree angles, which again is 60 degrees, and at the base we get two 90-degree angles because it's an altitude. Both of the triangles that it's been divided into now are 30-60-90 triangles. Suppose half of the bottom side is x. That means from the altitude over is x. That means the other half is also x, and the entire side has a length of 2x. This means that the hypotenuse is going to be 2x because all sides of an equilateral triangle are the same. Now, if we just look at the 30-60-90 portion of it, or this portion, what we have is one side that's x, a hypotenuse that's 2x, and the missing side we'll call the long leg because it's across from the 60-degree angle. It's going to be longer than the angle, than the leg that is across from the 30-degree angle. Now, using Pythagorean theorem, we can figure out what that missing leg is. It would be x squared plus the long leg squared has to equal the hypotenuse, or 2x squared. So x squared plus the long leg squared equals 4x squared. Subtracting 1x squared on both sides gives me the long leg squared equals 3x squared, and to complete the problem I need to take the square root of both sides. Well, the square root of the long leg squared is the long leg. The square root of 3 is just the square root of 3. The square root of x squared is x. Now, taking it and using the simplest numbers that we possibly can, what that means is that the short side of our triangle in the simplest form would be 1. The hypotenuse is going to be twice as long, so it's 2. And then following through with the Pythagorean theorem, we would come up with the long leg is the square root of 3. This is going to be our parent triangle. We're going to use this to set up each of our proportions to find missing parts of other triangles. So let's take an example. First, on the left we have our parent triangle. I know the short leg is 1, the hypotenuse is 2, and the long leg is the square root of 3. I have another triangle where I can see that the short leg is 4. I'm looking for the long leg, which I have listed as A, and the hypotenuse, which I have listed as C. And I can see from my parent that the 1 on the parent triangle matches with the 4 on my new triangle, and the square root of 3 on my parent triangle matches with the A on my new triangle. So solving this with cross products, I get A equals 4 times the square root of 3. So I know the length of my long leg is 4 times the square root of 3. Now I'm going to find C in the same way. I know that 1 on the short triangle matches with 4 on my new triangle, in the same way that 2 on my parent triangle is going to match with C on my new triangle. Solving my cross products, I'm going to get C equals 8. I would like you to try the next two problems, pause the podcast, then come back and check your answers. On the first problem, I matched 2 with 18 because they were the hypotenuses. And so the square root of 3 matched with p. Set up my proportion. You can divide constants with constants, and you can divide radicals with radicals. So I was able to divide the 2 into the 18 and get 9 square roots of 3. When I was solving for q, I still matched 2 with 18. That was my matching pair of sides. And from the parent, 1 matched with q on the new triangle. 2q equaled 18, so q was 9. On the next set, I knew that the long leg was 7 square root of 3, so from my parent triangle, the square root of 3 matched with 7 square root of 3. In the same way that 1 matched with j, I did my cross products, got the square root of 3 times j equaled 7 square roots of 3, divided by the square root of 3 to get both sides equal, and ended up with j equals 7. Again, you can divide square roots with square roots, you can divide constants with constants. On the next problem, I had the square root of 3 still matched up with 7 square roots of 3 from the parent to the new, and 2 on the parent matched up with k on the new, so I ended up with the square root of 3k equals 14 square roots of 3, divided by the square root of 3, and got k to equal 14. The process is the same no matter what these problems are, but sometimes they can get a little bit trickier. Here is an example of a problem that was a little bit trickier. Again, my parent is always the same, 1 for the short leg, 2 for the hypotenuse, square root of 3 for the long leg. And this problem, you can see that the square root of 3 on the parent is going to match with 9 on the new triangle. And this is where it gets a little bit tricky, because when I solve this problem, I have 9 matching with the square root of 3 in the same way that d matches with 1, that's the short leg. And when I did my cross products, I ended up with the square root of 3 times d equals 9. That meant I had to divide by the square root of 3. Pretty easy to get to the point where you have 9 over the square root of 3, but this is where you need to remember your Algebra 1. We're not allowed to leave a square root in the denominator of a fraction. To get rid of it, we do what we call rationalizing the denominator. What I wanted to do is I wanted to take that ugly little square root of 3 and turn it into something that was pretty. For example, the square root of 9. To turn a square root of 3 into a square root of 9, I had to multiply by an extra square root of 3. If you do it to the denominator of a fraction, you also have to do it to the numerator of a fraction. This is because this is like multiplying by 1, which changes the appearance of the problem, but it doesn't change the value. Following this multiplication, I had 9 square roots of 3 over the square root of 9. I was then able to take the square root of 9 and get 3. And then, because these are both constant values, they're actually coefficients, I can divide the 3 into the 9. It goes 3 times. And my answer is 3 square roots of 3. I did exactly the same process with finding the hypotenuse. In this case, 9 matched with the square root of 3 the same way that e matched with 2. I set up the cross products, did everything exactly the same. I reached the point where I had to rationalize the denominator, so I multiplied by a square root of 3 over a square root of 3. That gave me a square root of 9 in the denominator. I went ahead, I took that square root and got 3, and then at that point I was able to divide the coefficients. 3 went into 18 6 times, so my solution was 6 square roots of 3. You can actually do this by a shortcut. On 30, 60, 90 triangles, you have to know a few different things. One is that if you know the short leg, then you can find the hypotenuse simply by multiplying the short leg by 2, and you can find the long leg by multiplying the short leg by the square root of 3. Now all this does is it keeps you from having to set up the proportion. The key is knowing the short leg, and you'll notice this on the other two ways. If you know the hypotenuse, the first thing that you have to do when you know the hypotenuse is you have to find the short leg. So going from the hypotenuse to the short leg, you divide by 2, and that gets you the short leg. Once you know the short leg, it's the same process. You multiply by the square root of 3 to get to the long leg. Now, the next situation is if you know the long leg, and if you know the long leg, we're basically going to follow the same idea. We have to get that short leg first. So the relationship between the short leg and the long leg is the square root of 3. So you're going to divide by the square root of 3 to get the short leg first. Then simply multiply by 2 to get the long leg. We're now going to go on to the other special right triangle, the 45, 45, 90 triangle. 45, 45, 90 triangles, by the way, are used more for roofs in the north. Think about why that might be. On a 45, 45, 90 triangle, if we let one leg be x, because the angles are equal, it means the triangle is isosceles, so the other leg will also be x. Solving with the Pythagorean theorem, we have x squared plus x squared equals the hypotenuse squared, or 2x squared equals the hypotenuse squared. Take the square root of both sides, and what we end up with is x times the square root of 2 equals the hypotenuse. This is the relationship that we'll be using for our parent triangle. Again, using the simplest possible value for x. The leg is 1, the other leg is 1, and the hypotenuse is 1 times the square root of 2, or the square root of 2. Now to solve these, we simply set up proportions exactly like we did for the 30, 60, 90 triangles. The difference is that we have 2 equal sides, so we have fewer problems that we actually have to work. Setting up our parent, my legs are 1 and 1. My hypotenuse is the square root of 2. Looking at my new triangle, one of the legs is 5. That means the other leg is automatically going to be 5. I don't even have to do any work. Now all I have to do is figure out what my hypotenuse is. So 1 from the parent matches with 5 from the new triangle in the same way that square root of 2 from the parent matches with my hypotenuse on the new triangle. Or hypotenuse equals 5 square roots of 2. And that's my answer. Try the next 2 problems, see if you can get them, check your work. The first example is not too bad. The square root of 2 from the parent matches with 6 square roots of 2 from the new, the same way that 1 matches with the leg. Set up your proportion, cross multiply, divide by the square root of 2. The square root of 2's cancel, and you get 6 for the leg. The second one was a little bit trickier because we had to end up dividing 11 by the square root of 2, and you'll notice what happens over here in the green. After we get 11 divided by the square root of 2, we had to rationalize the denominator. So I multiplied by square root of 2 over square root of 2. This gave me 11 square roots of 2 over 4. The square root of 4 was 2. So my answer is a little bit ugly. It's 11 square roots of 2 over 2. Now, again, there are shortcuts you can use. If you know one leg, it's pretty simple. All you have to do is know that the other leg is going to be equal and multiply by the square root of 2 to get the hypotenuse. If you know the hypotenuse, it's a little bit trickier because the first thing you have to do is divide by the square root of 2 to get a leg. But once you know one leg, the other leg is exactly the same. This concludes today's podcast on special right triangles.